Right. Uh, Hello, I'm Nathan Gerken,
And I'm Ryan Masselink.
and we are here to talk to you about coding standards. So to start, I want to play a game we're all familiar with, Would You Rather? And the question is this: would you rather create new code or fix broken code? Now, a lot of us, I would imagine, would say that they would rather create new and shiny code, which is great. But there are also those who would rather dig in deep and figure out the really deep-seated issues plaguing your code. And that's fine too. But no matter what side you fall on, coding standards will help with both. By using coding standards, while you create code, you will prevent future maintenance issues and also making other maintenance issues easier to find and debug. This saves time, money, and effort. So, you now might be asking, why should I use coding standards? Coding st- oh, oops. You might be asking, why should I use coding standards? Coding standards help make your code more maintainable. This means that anytime you revisit code, it will be easier to fix. Coding standards also help give your code a more consistent look and feel. Additionally, they organize your code and reduce complexity. And all of these come together to make your code more readable, and code that is readable is easier to debug. And a common theme we will see throughout the rest of this presentation is if you put in the time now, you will save the time later. So, in essence, at Platinum Edge Solutions and coding standards can be boiled down to a few roles. At Platinum Edge, we like to refer to these roles as the prime directive. Rule 1, code should be human readable. This means we need to understand the code. The computer will understand it regardless. Therefore, it's more advantageous to make the code in such a way that in 6 months, 2 years, whenever you come back to it, you'll be able to read it and it won't be too complex. Rule 2, code should be easily maintainable. No one wants to go back and fix mistakes. But if you do, you want to ensure that any fix will be easy to figure out, and assume that you will need to go back to code later and reduce the headache that you might face later. Rule 3, code should be self-documenting. Any code you write shouldn't need a manual to understand. If you understand the language, you should understand the code. Again, just like the last rule, take time now and save the headache later. So we're going to start from when we're creating extensions, building up from scratch, from the base up. And we're going to be talking about the smaller things like variables and methods, and keep getting bigger until we get to class structures. So, to start, naming conventions. This applies to variables, methods, and classes. All three should use camel case and have intuitive names and not use single-letter variables. And only classes should be capitalized. This might take a bit longer, but when you come back in 6 months or more, the variable names are going to make a lot more sense. And if you need to do maintenance, descriptive variable names will save you a lot of time on their own. And have some snippets of code here. What I've shown is that, so these two snippets of code are the same. The one on the left, I took and I put as many single letter, non-descriptive variable names and methods as I possibly could. And the one on the right has more descriptive, easier to understand variable names. And if you're just like coming in, looking at this code, you're going to be able to understand the one on the right a lot quicker than the one on the left. Now, one thing to note, creating descriptive variable names isn't always easy. Sometimes you might give a variable a name the first pass, but then realize that it doesn't quite describe what you want it to. And that's fine. You can, as long as it's not released yet, you can always go back and rename that variable. So don't be afraid when you're naming these variable names to get with a coworker and say, hey, does this make sense to you? So next, methods. Try to limit each method to a singular focus. If a 3D rendering has multiple things that go together, make separate methods for each. If you have stretching logic, make a method for each line that needs to be stretched. You might find that some things are the same code, but repeated with slightly different inputs, which will lead to less repeated code and increased readability. In general, if you feel like you might need an inline comment, consider making it a method instead. The method replaces the need for an inline comment and makes things easier to adjust for child classes. And to illustrate this, I've taken the code from the previous slide and broken it further into methods. And what we see is we have a method for each piece of the 3D that gives us a very clear idea of what's happening in this code. Next, method and section headers. Methods and section headers give clear indications on what code does and what code goes together. A method header is a great way to separate and document methods, and section headers group together similar methods. This can save a great deal of time later debugging, because I know if I need to debug stretching, I go to the stretching section. And then once I arrive at another section header, I should have either found the issue or determined that the problem lies in another class. This is a very excellent example of take the time now, save the time later. And here I just, very basic example, show an example of section and method headers. Now, classes. You generally want to limit yourself to one class per file. This not only helps with organization, as normally classes will be in a file of the same name, but also prevents mistakes later when debugging. For example, if you have two large classes in the same file, you might, when you're debugging, the first one end up scrolling past the end of it and into the second one, and then start fixing code there and wondering why it's not changing in the first one. However, there are exceptions to the rule of one class per file. And at Platinum Edge, generally, if you can see two classes in a reasonable sized buffer, then it's okay. And as an example, this is an example of composition classes, and each one is there to return a different value for num files.
All right, so when we're creating stuff, before you write any code, you want to make sure you have a class structure in mind. Look through available documentation, think about the entire implementation before you start anything. Like on a whiteboard or I guess your whatever medium of choice, diagram the class structure you're expecting to create, and specify the class in which certain fields or methods are going to be used in, and see where it's common and kind of adjust as you're adding more in there. Think about common parent classes and how those can help simplify in the future, where like in this example here, we have corner surface with the 90 degree and 120 degree surfaces as the children for that. And this corner surface class might not actually have any code in it. It's just there to be a use for like checking things later. So if we if we do or let's say the manufacturer says like there's no connections to panel frames for corner surfaces, just cause. Then the corner surface class that we added, we can use that for in if conditions inside the animation try snap, and just do the top one there and say if it's in corner surface, return false because we don't want to connect. Otherwise, you have to do every single one listed out, and if you add more later, you have to make sure you come back to this to update the code. And it's just easy to forget, and extra spots where you have to spend more time. And I know planning out stuff can feel unproductive, like you're not in front of a keyboard, you're not typing, so you don't feel like you're getting anything done, but it ends up saving development time in the long run, and it can help just make the code more consistent, more readable, less duplicated code, because like I don't like fixing bugs, so I really don't want to do it twice for the exact same bug. Go. Next slide.
Use the down arrow.
There we go. So when we're creating code, sometimes classes can start to get out of hand. Just compiling a bunch of code in there especially for complex calculations or some operations. When this occurs, we can move all that code into a calculation environment, and ends can be easier to debug because all the related code for that section is in the same file. So if something goes wrong with that operation or calculation, you know exactly where to go to find it. It's not just kind of like strewn about in multiple levels through different methods and throughout your snappers. And no. Yeah, arrow keys maybe?
Yeah.
There we go.
That's
Oh, too many. There we go. So this is just a simple example environment, just a couple fields on it, constructor that sets those fields, and then just a main method in here that, I mean, it doesn't do anything important, but we're just kind of doing a few things in there, just invalidating snappers just to simulate something taking a while, just because doing anything more complex in there just, I mean, it's an example. It doesn't really help us. But we'll come back to that later. That'll be used for our example that we're running some stuff through later. But next we get to, all right, environments, they sound neat, right? But when do we use them? And that's just an impossible question to ask or impossible question to answer with like definitive steps and saying, yep, this is always in this case you always want to use it, and this one you always don't want to. So the best way we can really look at this is through pros and cons. So first pro of using them is complex calculations and operations are contained in their own file. Makes stuff easier to read. One of the cons is it adds additional files, which takes a little more time to look through sometimes, where you think, all right, it must be with this snapper that I have to go to, and you look through all the child classes and don't find anything, and then realize, oh, there's an env declared in it, and I didn't see that at first. one of the pros is environments can be used across multiple classes, so almost as close as you can get to interfaces, which maybe we'll get them eventually, but probably not. So this is what we have. It can increase debug time if it's a super simple thing. Like if you're just adding two numbers together, you don't need an environment for that. That's pretty obvious. But if it's too simple, then it just adds more complexity with extra files and making sure that the env is declared right and used right. And yeah, it can add stuff if it's not complicated enough. They can help reduce the amount of duplicated code, kind of consistent theme across here. So one thing that can be a drawback is instantiating the environments. It can take a little bit of time. But depending on what you're doing, it may be not as much as you might think, and that's where we're going to come back to that example we saw a little earlier, doing some timing on those to see actually how long it takes. Another thing that's nice about environments is they can be extended, which makes them super versatile and easy to build off of. But another con is they can be extended, so it makes it more complicated. Just where you think, oh, yep, it's got to be in this file, and you look through it and don't find anything, and then you actually print off the environment field, and you're like, oh, wait, that's a different class than what I'm looking at. I didn't realize there was a child. Next question is, should these environments be persistent? This is somewhat an opinion thing, but in our opinion, short answer is no. We don't want to keep them around. They're used to calculate something in an exact snapshot of time, and then we can just throw them out once we're done. Getting rid of them ensures that all fields inside of it are cleared. You don't need extra code to reset or update or worry about making sure that you're actually getting the right result because you have some old data in there that's getting in the way. You can make sure that file sizes stay smaller by, if you have them as fields in classes, make sure they're stream null. And throwing them out also reduces the memory footprint of CET. Just not keeping them around, they get garbage collected. But kind of as I hinted earlier, you're thinking, all right, Mr. Presenter. In the last slide, you just said that a con of these is that they can take longer if you keep instantiating them, and I'm saying throw them out every time. And why do we recreate them every time then? And that's a fair question. So although creating objects inside of CET does take some time, it really isn't that bad, and in most cases it's going to be negligible. So the environment from earlier, nope, one too far. But yeah, this example from earlier, we're going to use that we're going to put some timing code in it, and then see what the actual results are for this. So we are going to be using some probes, which if you don't know what those are, they're extremely helpful. And I learned about them with a webinar from Paul. I don't know if they're doing any more of those anytime soon, but if they are, you should attend because it's extremely helpful. Otherwise, I think the presentation might have been recorded, so you can probably talk to Paul and find it. So yeah, that's what these are here as probes, where we just give it a name, and then everything that's inside of there gets kind of tracked as to how long it takes. Even if you call it multiple times, it just kind of stacks it up in there. So at the top, we've got the no persistence method, where we have the environment being instantiated inside the for loop. So every single time in the 10,000 calls that happens there, the environment's going to be reinstantiated and recreated. And then in the bottom one here, we have the creation of that environment outside of the for loop. So it happens once, and we go through. So yeah, that's where we're instantiating no persistence, and that's where we have the persistence. And this is just the example test code that I wrote just to kind of wrap everything up, init the probes, call both methods, and then use the probe reporting. So here's the results for this. Might be a little tricky to see, but down here is where we instantiated the demo environment with no persistence. And out of the 2 seconds of time that it took to loop through those snappers, it was 2 milliseconds of time inside of that instantiation for 10,000 calls. So that's like 0.2 microseconds per call. It shows up as 0 on there because it rounds it down. We could do this, I think it was like 4.1 million times in a second. So unless you're doing an operation 4.1 million times a second, then yeah, maybe you don't want to make these desistent. So, I mean, if you're doing something 4.1 million times in a calculation, you're probably doing something wrong. And then down here is just the other case where we instantiate it once, and I mean, it all rounds down to 0 because it takes almost no time to actually declare this. So kind of the takeaway from this is, yeah, it takes a little bit of time, but like, it really doesn't take much. You might as well just get rid of them because it simplifies things, reduces your memory footprint, just gives you a lot of other benefits that most of the time is just going to be better to get rid of them. But I mean, in some cases, if you're creating an env and right as you create it, it does a bunch of calculations and those are going to stay consistent for a while. Sure, save it, keep it cached. You can know if you need to cache it just by doing some of these timing analysis on it. And so I'm not saying every time throw it out and just remake it, because sometimes you'll want to cache stuff, but majority of the time, probably can just get rid of it and remake it every time. So overall, for creation, you spend more time reading and interpreting code than you do writing code. By a large margin, you're going to be reading more. So take the few extra seconds to make it constant, to break something out into its own method, plan out your class structure, and whatever else. It's going to save you time in the long run, and it'll make your life easier and when you inevitably have to maintain some of the code that you create. Future you will definitely thank you.
All right. Now we're going to move on to code maintenance, which is when we go back to code that's already built. And a great rule here is always leave code better than when you found it. We all make mistakes, things happen, and sometimes we don't follow the coding standards, and things get missed. But when you go back through code, you might see something that isn't up to standards, like a single letter variable, or a method missing a header, or section headers. When you see these, make a habit of taking the time to correct them, because remember, a few minutes now can save hours later. And in general, you want to leave code better than you found it. So, what are some of these things we can do? Well, use constants instead of hard-coded strings and numbers. This is especially helpful if the values change, mainly because if you have to change the values individually, you need to change them everywhere you used it. And who knows if you got them all, if you missed some, if you changed some that were the same value but unrelated. Using a constant can save a lot of this headache and ensures that any changes will be to the right things. And as with variables, ensure that names for constants make sense. Properly naming the constants will also document them as well. So as an example, on the left, I show an example of a code block that doesn't use constants. On the right, I show one that does. The one on the right is in general much cleaner and has the same meaning as the one on the left. Additionally, if you use these constants elsewhere and they need to be changed, as I already pointed out, you have a single point where if you, for instance, need to change a code, you go to wherever that's declared, change it there once, you're done. It makes the whole process a lot less confusing and will save hours on down the line. And I can't stress it enough, take the time now, save the time later. Spacing. Use spacing in general. It makes the code easier to understand. One thing I was taught when I first started working in CET was we don't pay per line. So you can use spacing. And examples I've shown on the left is where spacing isn't used. On the right, it is. And it's a whole lot easier to read the code on the right and understand what's going on than it is the code on the left. Write logical code. Break up complex statements. If something seems too hard to easily understand, break it up into multiple lines or methods. As an example, I made a quadruple stack ternary. And to illustrate how hard that is to understand, when I first made that and was writing the what it is in if statements, I got it wrong the first time. I got it backwards. So those things make it simpler. Next, be consistent. In general, use brackets or braces for if statements. The only exception is one-line return statements, but even then, use brackets. It makes it a lot easier to debug because if you need to debug, you hit enter, put your debug code, you're done. If you didn't put the brackets and braces previously, you need to add the brackets, hit enter again, add your debug code. Takes a bit more time. It's a simple thing, but I've gotten into the habit of when I write an if statement, after I write the condition, I put both brackets right away so I don't forget them. And an example here, the ones on the left, don't do that. The ones on the right, that's how you should. It's a lot easier to debug this. Also, if you have a method that returns something, like this, use a temporary local variable. It makes it easier when you need to debug to hit enter, put your debug code, print the value if it's not coming back right, and figure out what's going on. At PES, we like to use res, which is short for result. But by doing this, you don't need to reshuffle the code like the one on the left. To be able to debug that statement, you have to put in a temporary variable for that, put return on the next line, take your code, and then return whatever your temporary variable is. Keep code clean. Remove comments that is just commented out leftover code. Keep the code in your class as relevant. Comments and commented code should be strictly for documentation. If it doesn't have a purpose, delete it. Remember, we use a code repository. So if you delete something and you need it later, you can go back in the repository and find it. I've done that before. Super helpful. And as an example, this code in this comment is documentation. We give a clear statement of what this is for, and you can also do this with, like, say you're doing a migration and you need code to be deleted later. You can put in a comment, hey, delete this after such and such date. In general, it allows us to just better document code and keep it relevant. Finally, code reviews. It's a great way to enforce standards. You essentially have someone else review the changes you made before you merge them in. That way you can make sure you're following standards and have someone to hold you accountable. It can also, some cases, help avoid mistakes that could ruin the code if not caught. Next, training. And when you train new people, everything from the first two sections comes back here. All the standards we talked about come together, and they help make a code that is self-documenting and easy for someone new to pick up and understand. At Platinum Edge, we're able to leverage this to our advantage and have a training process that's self-guided. This saves a great deal of time because new hires can teach themselves, and they don't need a more senior developer to watch over their shoulder as they learn the code. We still need to answer questions for new people, but in general, it tends to be for the more complex things. And we all know sometimes developing in CET isn't always intuitive, but adhering to the coding standards coupled with the vast documentation of CM that we at PEZ have created, we've cut off months off the training time that it takes to get new hires up to speed. So to close out, questions? Any questions?
How similar is this, like coding standards in C#?
So I guess, just in case, the question is how similar is this to coding standards in C#? It's been so long since I've been in C#, I don't remember.
More of a comment than a question. When you were talking earlier about designing your class structure and preparing for children and all that, one thing we've really noticed in the past is ask as many questions as you possibly can about what you're building.
Yep.
Usually you're going to get a snippet of build this, and you don't realize that there's 7 other things that are similar to it that you're not being told about. And so you build it, and then they're like, oh, now build this. Why didn't you tell me about that? 'Cause people giving you information aren't going to necessarily know
Yep.
what's going to help you. So if you can ask as many questions as you possibly can and learn about even high level, it'll
Yeah.
help a lot.
Yeah, gathering requirements is a skill in itself, really. Yep. Yep.
Another comment on like constant usages I've found too, like if you don't use them, sometimes it's hard to know, are these intended to intentionally be the same thing or not, or
Yep.
just coincidentally the same thing. So if you have
Yeah.
multiple constants that might have the same value, then that also signifies to yourself in the future, right? Hey, this 50 inch here isn't really meant to be the same as this 50 inch
Yep.
here. So when you need to change something, right, you can tell, hey, I intended for those to be 2 separate.
Yep. Yeah. You
Yeah.
just.
Same value, they represent different things. So it's very been helpful for me in future self.
Yep. Yeah.
Yeah.
You can't just do a find replace on every single 50-inch in the code and be like, "Yep, we're good now,"
Yeah.
because you're gonna run into some troubles probably.
So, any other questions?
Your example M, you had fields in it. Do you guys ever write M's that are
You can, yeah. Like,
Do you still keep them and make sure they're not persistent?
it really can go either way. Like, if they're just entirely stateless, have no fields, then sure, you can just make it, store it, just because it's never going to change, so you don't have to worry about any of those drawbacks of making sure that things are updated or whatever. But still, if it's got no fields, it's going to take almost zero time to instantiate it anyway, because it's not really taking anything to make it. Where for these, I put fields in that one just to like show that, yep, creating and allocating memory for that stuff does take a little bit of time, but it's almost none. But without that, it's actually like none. But I mean, the desire to be efficient in as many places as you can, I understand that. So like keeping it cached and just if there's nothing changing about it, then yeah, there's no reason to get rid of it.
Anyone else? All right. Well, thank you. And enjoy the rest of the conference.